Hello, AP Chem kids. This is going to be a lesson on polyprotic acids and how to calculate pHs and concentrations with polyprotic acids. I am starting this video though with a Ka table just because I want to remind you guys from your first year course you do have a Ka table. So if you are still have access to that, you can pull this thing out and you can look at some of the Ka values. AP is not going to have you to memorize these. They will give you always a Ka value if they're asking you to solve for something else. So that information will be presented for you for this Ka. So just wanted you guys to kind of see that. But also, in this table, it is just showing the first protonation of the acid, okay? So acids, and here that's kind of a fun word, protonation. Protonation means how many protons will be dissociated in the fact that it's dissolved in water. And the thing about acids is that they will protonate, and some acids can furnish more than one proton to the solution. And for that reason, we call it a polyprotic acid. Poly meaning more than one. You know, we can actually have, I think you probably heard about that from one of Renee McCormick's videos, is that you can have diprotic acids and triprotic acids. Polyprotic acids is really just kind of a generic term to mean more than one. So here I have the equation for carbonic acid, and now what will happen is that carbonic acid will protonate one hydrogen at a time. So the first, and we actually will say words like this, the first dissociation will have its own unique Ka value. And then the second protonation, so taking off that hydrogen, would have a second Ka value. And in your textbook on table 14.4, you can see there is a stepwise dissociation constant for several common polyprotic acids. And if you looked real closely here, you can see carbonic acids. So their values are right there, okay? Notice that the first protonation is larger than the second protonation. And for a triprotic acid, the third protonation would be even less than the second protonation. So here's an here's my example. Here's phosphoric acid. The first protonation for phosphoric acid is 7.5 times 10 to the negative 3. Remember, I'm telling you guys, you kind of got to like pay attention to these orders of magnitude. Most of the hydrogen ion in phosphoric acid, which by the way is in soda pops, most of that hydrogen ion comes from the first protonation of the H3PO4 species. You can see that when you get to the second protonation or the third protonation, look at those orders of magnitudes. You're not going to expect a lot of the hydrogen coming from that. And that's really typical no matter what the species of acids are. Usually the first protonation is the one that gives you the most hydrogen ions. All right, and this is an example now of a polyprotic acid. Phosphoric acid. We're going to use that. We're going to use the K, so we have to remember these Ka values. So if you're seeing that I'm putting Ka values in, you're wondering where I'm getting them from. I'm getting them from the table. These are the values right here. This is an example in your textbook that's asking you to find the pH of a 5 molar phosphoric acid solution and the equilibrium concentrations of basically all the species that would be in that solution after equilibrium has been established. Okay, so when we look at this, the first thing that I know I have to do is I'm going to have to do a rice table because I need to find the hydrogen ion concentration of that first protonation, because the first protonation is what's going to give a majority of the hydrogen ions. So as I do that, I'm going to move this to the side. I write my equation. So the phosphoric acid is going to dissociate into hydrogen ions and H2PO4 with dihydrogen phosphate ions. And I fill out my rice table and I calculate my Ka. Again, where did I get this Ka value of 7.5 times 10 to the negative 3? From the table right here. If you don't believe me, there it is, 7.5 times 10 to the negative 3. is equal to, again, the equilibrium line, which would be x times x over 5.0 minus x. I can assume that that x is so small that I can solve it the easy way, and in fact I do, and x becomes 0.19. That's the hydrogen ion concentration. So one of the first things that they asked us to do was to find the pH. So finding the pH is 0.72. So notice I'm showing the substitution. I just can't write the number 0.72 down. The AP board won't like that either. You need to show the substitution, and that's also required for my test. So pH is equal to the negative log of 0.19, which gives you a 0.72, and voila, we got one test done, okay? Now, the other thing that's important to recognize here is that this H, so I'm going to highlight that X, which we were solving for, which was 0.19 molar, okay, is also then going to equal the H2PO4 concentration. Okay, so the H2PO4 concentration is going to be the same as the first protonation hydrogen ion concentration of 0.19. And I should have behind here a capital M, okay? So I know this concentration is to be 0, oops. I'm gonna see if I can erase that. No, I can't. Let's see if I can get rid of that. No, I can't. So I'm just gonna deal with it. So this is 0.19 M, okay? And I'd also have to know the H3PO4 concentration at equilibrium. Well, the H3PO4 concentration was originally 5 molar. And so if I subtract the 0.19, because that's the amount of hydrogen that was dissociated, so basically all that I'm doing is I'm just filling out this piece right here. And that's going to give me a value of, just with sig figs, 4.8 molar. So this concentration is 4.8 M. That's the concentration of the H3PO4. Sorry, it's messy. I can't do anything with my iPad and my stylus pen that I have. This is the best I got. Okay, so now I would have to calculate the H2PO4 minus concentration, and that will come from the fact that, let me just see, I'm going to hit pause here for a second and I'll be right back. Okay, I had to pause there because I had to write the second dissociation reaction that's happening here. And so here it is. The H2PO4 is going to dissociate into then H plus plus the HPO4 2 minus concentrations, or a reaction. And if I were to write this Ka2 expression, because this is the second dissociation, I would write Ka2, so notice I put a little 2 there, is equal to the hydrogen ion concentration times the HPO4 with a 2 minus concentration all over the H2PO4 minus concentration. Okay? So now you could do the Rice table for this, and it is actually probably presented in your book that they do the Rice table for this, but what thing is interesting is that for that second dissociation, the hydrogen ion is going to be equal to the H2PO4 concentration. So since that hydrogen ion concentration, which we know is, I think I can even do this, we'll do this with a different color. We know that this is 0.19, right? We know that the H2PO4 is 0.19 molar, so both of these are molars. These will cancel out. And so we can say that the Ka2 value, which you know from right here, the Ka2 value is 6.2 times 10 to the negative 8. That Ka2 value is equal to the HPO4 concentration. So Ka2, which is equal to, Ka2, which is equal to 6.2 times 10 to the negative 8 is also equal to that HPO4 2 minus concentration. So that would be in molarity. So that will now be what we can put right here, 6.2 times 10 to the negative 8. Oh, I should have a negative 8 there. There we go. And then please put M's behind here. It's very hard for me to do that. So now we've got the H2PO4 concentration as well. The last thing that we would have to do, and I'm going to have to add another page here, is then to calculate the H3PO, or I'm sorry, the PO4 3 minus concentration. So just give me a second. Okay, so the last piece then was to calculate the phosphate ion concentration. So for that phosphate ion concentration, and I can see I already have a typo in here, that the Ka for the third dissociation is 4.8 times 10 to the negative 13. And when I set that up to what would be the equilibrium line expression, you will see that now, again, that hydrogen ion concentration of 0.19, where does this come from right here? This comes from the first dissociation. Remember, that has such a high value. The dissociation that you would get from the second protonation is so small. And in terms of significant digits, it's not even part of the worry. So that's where the 0.19 comes from. The 6.2 times 10 to the negative 8, that was the concentration that you found here, if you'll notice. That's what we had found was the concentration of the HPO4 2 minus. Okay, so that would make sense. So then all you have to do is solve for X to find the phosphate ion concentration, and that ends up being 1.6 times 10 to the negative 9 molar. So you just calculated the pH of a polyprotic acid and all of the concentrations that would be available at equilibrium. I hope this helps, and good luck.